Welcome back to this unit on advanced force and torque closures. We now look at van der Waals and so-called JKR cohesion force closures. Let us start with van der Waals forces. These forces are electrostatic forces on a molecular level. One distinguishes between the following types of van der Waals forces. The first type is the so-called London or dispersion van der Waals force. These forces are caused by a so-called induced polarization of non-polarized molecules. So non-polarized molecules are a huge range of all molecules that exist. What we mean with induced polarization? This is because as molecules approach, and this is also true for molecules making up two different particles, their electron clouds shift slightly and very quickly, and they produce temporary dipoles, which are, if we average over time, net attractive. You have seen this cartoon already on the overview slide. Important for you is a dipole is nothing else as a molecule or a part of a molecule that has a spatial separation of its charge density. In short, there is a region with a higher amount of electrons, so here are more electrons, and here in this part are less electrons. Of course, this is for a simple water molecule. However, we can also see this in many other molecules. To sum up, the London van der Waals forces, they exist between almost any type of particles and they cannot be switched off. Please note that in most textbooks, van der Waals forces are used solely to describe London forces. We will also do the same in the following. So when we talk about van der Waals forces, we always mean those London van der Waals forces. There are two other groups of van der Waals forces, which are Keesom forces. They exist between molecular dipoles. We will not discuss them, same as the so-called Debye forces, which are the interactions between polar and non-polar molecules. We can distinguish between two groups of van der Waals cohesion forces. The first group are van der Waals forces, or London forces as we have learned, for infinitely stiff particles. Here, the interaction does not depend whether the particles penetrate each other or the particles deform because they are soft. You can say they are contact independent van der Waals forces. We will see in a second that this is not really true, but to a very large extent. So if we look at these force models, there are very old developments, theoretical calculations that allow us to predict the force between two spheres. What you're going to see are simplified relations already, however they are widely used. So what we do here is we consider two spheres interacting with these London van der Waals forces. The key influence parameter on these forces is the surface-to-surface distance t. This is shown here on this equation here. You see the van der Waals force is inversely proportional to d squared. So it's a very strong dependence on this surface-to-surface distance. Please note that Ri and Rj are the radii of these two interacting spheres, which can be generally different. However, if they are the same, we arrive at this very important expression for the van der Waals force between two particles with the same size. It is now important to note that we need two cutoffs for t in a DEM-based simulation. And the reason is that if d approaches 0, this expression diverges. So we need a cutoff for the minimum distance that we allow in our force calculation. This distance can be based on roughness or on other aspects. Don't forget that we have always a neighbor search grid. that means we also must employ a maximum cutoff for D. And the reason for that is very simple. If we don't cut off at a certain large D value, the current position of the particles in the search group would determine whether we'll calculate the van der Waals force or not. And this is something that is a not clean way of making calculations. One can also define a van der Waals force for sphere-wall interaction. This is simply the limit where this Rj approaches infinity, and it's easy to see that then we arrive at this expression here. Also here, an important note. You see already that sphere-wall interactions are twice as strong as sphere-sphere interactions. You see here the Hammaker constant A ham divided by 12 and here divided by 6. Let us now look what happens if particles are soft, as in the classical DEM, and for example overlap with a wall. Of course, we have seen that the van der Waals force will be non-zero if the particles don't contact. That's why we need a special consideration of the search grid. However, what shall we do when the particle is interpenetrating with this wall? Well, what we do simply is we bound the distance d, which is nothing else as the negative normal overlap, by a minimum distance d min. And then we simply calculate this van der Waals force based on this minimum separation distance d min. Thus, you see that large overlaps delta n do not increase f or affect f in any case. Thus one could say this is a contact force law independent force closure. However, recent work shows, and nicely illustrated, that this is not true because particles dissipate energy when they overlap, and the van der Waals force, this quantity, has an effect on this dissipation. For details, please look at the publication of Gu et al. So this van der Waals force model is not perfectly contact independent, and we need to take into account the softness of the particles when we do DEM-based simulations. Let me now finalize this part of this unit by 3 important statements related to the Hammaker constant. First, this constant depends on 3 materials in contact, namely the 2 particles or the particle and the wall, and the fluid in between the particles or the fluid in between the particle and the wall. So you have to be always careful when looking up Hammaker constants. Second, note that these Hammaker constants are in this order of magnitude. So this is very small. However, if you do the calculation as I've shown you before, you will see that these small energies lead to forces that are much higher than gravity for particles that are smaller than, let's say, a couple of millimeters. Finally, it's important to know that this distance of the surfaces has a big effect. As already shown at the beginning, roughness is important. Thus, rarely one takes Hammaker constant from a textbook and puts it into this calculation simply because the roughness is not known. Here, calibration is a much more useful approach, as will be shown in one of the units. With that, I would like to close this part. See you next time.